this example, an electron gun creates a beam of electrons moving with a speed of 0.1 c, so 0.1 times 3 times 10 to the 8 meters per second, moves through a parallel plate capacitor with an electric field strength of 50,000 newtons per coulomb. By how much does the beam deflect as it passes through the capacitor, where the plate spacing is 0.5 centimeters? So the distance between the two plates, D, is 0.5 centimeters. So we have some electrons entering this region. The first thing to ask is, what does the path even look like? It's important to get that in your head before you ever get started. So the electrons come in moving horizontally. There's our initial velocity. If we want to know what the path looks like, we have to think about what is the force. Well, let's remember the relationship between force and electric field. This is a charge in an electric field, so it feels an electric force. So the force on the electron is the electric force. And the electric force is equal to the charge on the electron times the electric field. The charge on the electron is negative of the fundamental charge. So the force and the electric field are opposite in direction because of this negative sign. That tells us that the force is up and the acceleration is up. That tells us that our path is going to be like projectile motion. So it's moving to the right, but it has a force that points up, therefore it's going to move in a parabolic trajectory. So this is a problem of projectile motion. So you can use all of your strategies from Physics 1050 or 1020 to solve this problem. The only step we're layering in is we can say that F is equal to charge times electric field to find our force. So in 1020, most of the problems you had that the force was gravity or weight. This time the force is electric, but the rest of the problem is going to be the same. So let's start by making a list of the things that we know. So let's write down our initial position. So x initial, let's call x initial equals 0, so we'll put the origin right here. X final is when it gets to the other side. And let's say that the length of our plates is given in our picture. It's 2 centimeters. So our x final is 0.02 meters. The initial velocity in the x direction, so it comes in horizontally, the initial velocity is 0.1 c. C is 3 times 10 to the 8, so v is 3 times 10 to the 7 meters per second. And our acceleration in the x direction is going to be 0 because our force is in the y direction. Okay, let's write down our y information. Y initial equals 0. Y final equals, we don't know. That's what we're trying to sort out. How far up did it move? Our v initial y is 0 because it comes in horizontally. AY is not something we know just yet, but we can figure out because we can find the force, which means we can find the acceleration. Okay, let's do AY next, then we can plug it in right here. So since we know that F equals MA, A is equal to F over M. We're just trying to find the magnitude here. We know it points up, so we already know that the direction is up, so we don't have to write in vector form if we don't want to. The magnitude of the force is the magnitude of the charge times the electric field divided by the mass. So the size of the charge is 1.6 times 10 to the minus 19 coulombs. Size of the electric field is 50,000 newtons per coulomb. Divided by m, m is the mass of the electron, 9.11 times 10 to the minus 31 kilograms, gives us an acceleration of 8.78 times 10 to the 15 meters per second squared. And the direction, we'll remind ourselves, points up because the force points up. So there's our AY. So that's our acceleration in the y direction. Where we're going to try and go from here is, let's write down an equation that's going to tell us how far it travels in the y direction. So let's write down our equation for position in the y direction. So our equation for position in the y direction is y final equals y initial plus viy times t plus a half times ay times t squared. This equation's okay. Y initial is 0. V initial y is 0. We want our y final. We know our ay. We don't know our t. So can we find our t? I would say yes, we can find our t because we know some information about x. So if we come to our x equation, x final equals x initial plus v initial x times t plus ax times t squared, half ax t squared. X initial is 0, ax is 0, so t is equal to x final divided by v initial x. Our x final was 2 centimeters because it goes the whole length of the capacitor. V initial x was 3 times 10 to the 7 meters per second. Tells us that our time is 6.67 times 10 to the minus 10 seconds. So our electron gets through that capacitor pretty fast, but it makes sense because it is going very fast. So now we have our t that we can plug in our y equation. So our y final is a half times our y acceleration times t squared to get a deflection of 1.95 times 10 to the minus 3 centimeters. And if you wish, you can write that in centimeters or millimeters. I'll write it in centimeters, 0.195 centimeters. Oops, that should have been meters. So what that tells us is that it doesn't deflect nearly as much as I've drawn here. It only deflects up about that far, and it won't run into the positive plate.